On April 13, 2026, a Chinese company called Geely held a press conference and announced something that engineers had spent decades calling physically impossible. Not difficult, not just expensive, but impossible. The number they put on the screen was 48.41%. And if that sounds like some dry random statistic, let me explain it in the simplest way possible. When your car burns fuel, most of that energy does not actually turn into useful motion. It escapes through the exhaust as heat, gets absorbed into the engine block, or disappears through the friction of metal parts constantly rubbing against each other. A normal car from top brands like Toyota or Volkswagen only uses about 30% of the energy in the fuel you put into the tank. The other 70% is almost completely wasted, turned into heat that gives the driver no real benefit at all. For more than a century, engineers have been trying to reduce that waste. And before this, the best thermal efficiency any mass-produced car engine had ever reached was only 41%. Toyota celebrated that milestone like a moon landing. They spent billions of dollars to get there, then told the world that this was basically the final ceiling, that going any higher would make the cost unreasonable and push the technology right up against the limits allowed by the laws of physics. But Geely walked past that ceiling as if it had never existed. This number was certified, officially measured, and recognized as a Guinness World Record. This is not a small step forward, and it is definitely not just a software update. It feels like an entirely different world of engineering. And the most shocking part is not even the number itself, but how they actually achieved it. The story involves a tornado inside a cylinder, an engine that is deliberately designed to run hot and cold at the same time in different areas, and an 11-in-1 machine that looks nothing like a traditional engine. But first, to really feel the weight of 48%, we need to understand why 41% used to be seen as the finish line, and why 40% was once considered a wall that could almost never be broken through. Imagine an internal combustion engine as a campfire trapped inside a metal box. You put fuel in, it catches fire, the explosion pushes the piston down, and that movement eventually turns the wheels. On paper, it sounds simple enough. But the problem is that fire creates a huge amount of heat, and heat does not care about your wheels. It wants to spread in every direction, into the metal walls, into the air around the engine, and out through the exhaust pipe. The engine is constantly fighting to force that energy into one useful direction, and most of the time it loses that fight. In physics, there is a limit called the Carnot limit. You do not need to remember the name. You only need to understand what it means in simple terms. Every heat engine has a mathematical ceiling for efficiency, and that ceiling depends on how hot the explosion inside is compared to how cold the exhaust is. The bigger the temperature difference, the more useful work you can theoretically extract. But both ends have limits. If you make the explosion too hot, you melt your own engine. If you keep the exhaust too cold, the emissions control system stops working properly. For decades, engineers at Toyota, Honda, BMW, and Volkswagen treated 40% like a brick wall. Going from 35% to 41% took billions of dollars and decades of careful refinement. Toyota got there with a smart trick called the Atkinson cycle, where the intake valve stays open slightly longer than normal. That small change reduces wasted energy during compression and squeezes out a few extra percentage points of efficiency. When Toyota reached 41% with its 2.5-liter dynamic force engine, the whole industry almost stood up and applauded. Many engineers published papers saying that going far beyond that level was basically not practical at any reasonable cost. The common belief at the time was that pure electric vehicles were the future anyway, so why keep pouring effort into a technology that was slowly being replaced? That assumption turned out to be one of the most expensive misjudgments in modern automotive history. While Western automakers were busy betting the future of their companies on fully electric vehicles, Chinese engineers were asking a completely different question. What if we started again from scratch? That question created the first crack in a wall that had seemed almost impossible to break, and it came from a name you probably already know. Before we talk about 48%, we have to talk about 46%, because that is where the story really starts to shift. BYD, short for Build Your Dreams, looked at traditional hybrid car design and basically decided that the old approach was outdated. In a standard hybrid, the gasoline engine and the electric motor both help send power to the wheels. The engine constantly changes speed, revving higher on hills, slowing down at traffic lights, and shifting through a complicated gearbox. Every time the engine speed changes, it moves away from the range where it works most efficiently. BYD had a different idea. What if, for most of the trip, the engine did not directly drive the wheels at all? What if it simply stayed at one perfect speed and worked as a generator? In that case, the wheels would be driven by electric motors, while the engine would do only one job: run at the exact revolutions per minute where it reaches its highest efficiency. Because the engine no longer had to chase road conditions, BYD could tune it extremely precisely for one single operating point. No major compromises, no unnecessary trade-offs. The result was their DMI system, which reached a thermal efficiency of 46.06% on the fifth-generation platform. The global automotive press was genuinely shocked. A 5% improvement may not sound huge until you realize that Toyota needed about 20 years and many billions of dollars to move from 36% to 41%. BYD did it in a much shorter time with a completely different approach. Legacy automakers had a quiet moment of panic, but then most of them returned to their old roadmaps and reassured themselves that this was just a regional story, that Western consumers would never accept it. They said the same thing about Japanese automakers in the 1980s, and we all know how that ended. But here is the thing. While the industry was still trying to process BYD's 46% figure, Geely had already been quietly working for 2 years on something that would make even that achievement look like a warm-up. And the key to what they created starts inside the cylinder itself, in a place almost no one thought to look. This is where the story gets truly wild. Geely's new IHEV system did not just improve the existing engine design, it basically tore up the old rulebook for how air and fuel mix inside a cylinder. This one's change is responsible for a huge part of that record-breaking efficiency number. The problem with a normal engine is that when air and fuel are pulled into the cylinder, they do not mix evenly. Imagine pouring cream into a cup of coffee without stirring it. You get uneven swirls, with some areas full of cream and other areas almost all coffee. The same thing happens inside a traditional cylinder. Some pockets of the mixture are too rich in fuel, while other pockets are too lean. When the spark plug fires into that uneven mixture, the flame does not spread everywhere at once. It starts at the ignition point and slowly travels outward like a wave. And while that flame wave is moving across the combustion chamber, heat from the first burning area is already leaking into the surrounding metal walls. By the time the whole mixture finishes burning, a significant amount of energy has already been lost into the engine block itself. That wasted heat is one of the biggest reasons traditional engines struggle to get past the 40% mark. Geely's engineers solved this with a vortex combustion system they describe as a fire tornado. They completely redesigned the shape and angle of the intake passages. When the intake valve opens, the incoming air is no longer pulled in passively. It is forced into a high-speed spinning vortex, almost like a controlled tornado right inside the cylinder. When the spark plug fires into that spinning tornado, the flame no longer crawls slowly across the chamber. It bursts outward almost simultaneously in every direction, because the fuel and air have already been thoroughly mixed by the turbulent spinning motion. The combustion becomes sharper, cleaner, and more synchronized. Most of the energy is pushed straight down onto the piston before the heat has a chance to leak into the cylinder walls. Less wasted heat, less pollution, stronger force on the piston, and higher efficiency. But when you push combustion that hard, a new problem appears immediately. The hotter and more compressed the explosion becomes, the greater the risk of engine knock. Knock happens when the fuel ignites by itself before the spark plug even fires, creating an uncontrolled blast that can crack pistons and destroy an engine in just minutes. This knock problem is exactly what kept engineers stuck below 41% for so long, and Geely's solution to it is just as clever as the tornado inside the cylinder. Every engineering textbook will tell you that running an internal combustion engine at extremely high compression and extremely high temperature is almost guaranteed to lead to catastrophic failure. You cannot keep pushing the explosion harder without risking the engine destroying itself from the inside. That was the wall the industry had been facing. That is why no one had gone beyond 41% in a mass-produced engine for more than 2 decades. Geely's answer was to make the engine run hot and cold at the same time in different zones, completely on purpose. In a normal car, the cooling system sends coolant through the whole engine at roughly the same temperature. It is a one solution for everything compromise that works well enough, but it treats the top of the engine and the lower block as if they need the same thing. In reality, they do not. Geely split the cooling system into 2 independent zones. The cylinder head, which is the very top of the engine where the explosions happen, is kept very cold. Coolant flows quickly and aggressively through this area, pulling heat away the moment it appears. Keeping the top cold helps the intake air stay dense and cool right up until ignition, which prevents early self-ignition and allows the engine to run at a much higher compression ratio than would normally be considered safe. A higher compression ratio means more energy can be extracted from every single explosion. Meanwhile, the lower engine block, where the pistons slide up and down thousands of times per minute, is deliberately kept warm. Why would you want part of the engine to stay hot? Because heat makes engine oil thinner. Thinner oil helps the pistons slide more easily and greatly reduces friction. Every little bit of friction you remove is more energy reaching the wheels instead of being turned into heat from metal rubbing against metal. So in the same engine, the top is kept cold to allow strong compression, while the bottom is kept warm to reduce friction. In traditional engine design, those 2 goals usually work against each other. Geely built a system where both can happen at the same time in different parts of the same engine. The whole process is controlled by an electronic water pump that reads engine conditions dozens of times per second and adjusts coolant flow almost instantly. It sounds like something that should not work, and that is exactly why it is so special. Other companies were not building it because traditional thinking said the trade-off was not worth pursuing. But even the most efficient engine ever created is only half the story. The other half is how to send all that energy to the wheels without losing it inside a complicated gearbox. And what Geely created to solve that problem is just as revolutionary. Even an engine with 48% efficiency becomes pointless if that efficiency is wasted through a heavy and complicated transmission system. Traditional automatic gearboxes are mechanical masterpieces, but they are also heavy and full of friction. An 8-speed or 9-speed automatic gearbox has hundreds of individual moving parts, clutch packs, hydraulic torque converters, shift forks, synchronizers, and many other components. Every single part absorbs a small portion of the energy you worked so hard to create. The entire system can weigh more than 100 kilograms and still waste a meaningful amount of engine power before that energy ever reaches the wheels. Toyota's hybrid system uses something called an electronic continuously variable transmission, a planetary gear set that was truly revolutionary when it first appeared in the late 1990s, but today it is basically an idea more than 25 years old. It adds weight and mechanical complexity that a modern hybrid powertrain does not necessarily need anymore. Geely looked at all of that and started again from a blank sheet of paper. What they built is called the 11-in-1 EDHT Intelligent Drive System. Instead of a gearbox in the traditional sense, it is an electromechanical power router. It packages the engine, the generator, 2 electric motors, the high-voltage inverters, and the thermal management hardware into one single compact unit. The total powertrain weight is reduced by 13.1% compared with traditional hybrid setups. There are no shift forks, no hydraulic oil channels, and no torque converter. For about 90% of daily driving, the internal combustion engine has no direct physical connection to the wheels at all. It simply runs at its ideal efficiency point and drives a generator. The electricity then goes either into the battery or directly to the electric motors that spin the wheels. From the gate, the whole experience feels like a pure electric vehicle, quiet, smooth, and with instant torque the moment you press the accelerator. Only under certain conditions does the system physically connect the engine to the axle, mainly when the vehicle is cruising steadily at high speed on the highway. At around 80 miles per hour and above, sending power through the electric motors can actually waste more energy than a direct mechanical connection. so the system automatically detects that situation and locks the engine to the wheels like a high gear, bypassing the electric conversion process to reduce losses. Managing this entire complex mechanism is an artificial intelligence system that recalculates the most efficient way to distribute power 50 times every second. It reads the navigation map, sees a hill coming 3 kilometers ahead, and decides in real time whether it should charge the battery now and coast down the other side later, or use the battery first and let the engine recharge it during the descent. It thinks about the entire journey in a way no human driver ever could. The combined result of all these elements, from the fire tornado combustion system, the separated thermal zones, the 11-in-1 drive unit, and the artificial intelligence power routing algorithm, is a certified fuel consumption figure of just 2.22 liters per 100 kilometers. This is a Guinness World Record for production vehicles. With a full tank of fuel, the driving range can go beyond 2,000 kilometers. This combination of numbers completely changes the conversation about what a car can actually become, and that is worth saying directly. The honest picture, pure electric vehicles are genuinely great in the right conditions. They are quiet, efficient, and produce no tailpipe emissions while driving on the road. But they also come with very real trade-offs that millions of car buyers around the world are still not ready to accept. A large electric sport utility vehicle needs a battery pack that can weigh more than 500 kilograms. Charging infrastructure is still thin across many huge parts of the world. And range anxiety is not just a psychological feeling. It is a real practical barrier for real people with real lives, real schedules, and real travel needs. Geely's IHEV system represents a completely different path through the transition period. You get the smooth, quiet, instant daily driving feel of an electric vehicle, but with a total range that can exceed 2,000 kilometers. You can refuel at any gas station on the planet. You do not have to depend on a charging network, while the fuel cost per kilometer can be comparable to a pure electric vehicle in many markets. What makes this even more remarkable is that the vehicle doing all of this is not some small lightweight city car. It is a full-size sport utility vehicle, yet it still consumes less than 2.5 liters of fuel per 100 kilometers in real-world conditions. For Western and Japanese automakers, this creates a genuinely uncomfortable challenge. The internal combustion engine was born in Europe, and Germany, France, and Britain dominated this technology for more than a century. Japan then refined it for 50 years to a level the world once thought was almost perfect. And now, the record for internal combustion engine efficiency belongs to a company that, 15 years ago, did not even have a truly serious global presence in the auto industry. Closing a gap like this is not something you can do with a software update or a new advertising campaign. It requires rebuilding engineering pipelines, asking different questions, and funding years of serious research. That is not an easy demand, especially when investors are pushing these companies to go fully electric. At the same time, their combustion technology is falling further behind. But for consumers around the world, this competition is actually good news. History shows that whenever this kind of engineering ambition enters the market, prices tend to fall and technology improves across the board. Legacy automakers will eventually have to respond. The only question is how far the balance of the market will shift in the meantime. What Geely has proven, beyond any single number, is that the internal combustion engine still has a lot of life left in it. The real limit may never have been only the laws of physics. It may have been the limit of what people believed was still worth trying. If you have followed this far, then by now you probably understand more about engine efficiency than most people who write about cars for a living. And honestly, that feels like a pretty good place to end. If you found this useful, hit the like button, subscribe to the channel, and turn on the notification bell so you do not miss the next breakdown. We will keep following this story as traditional automakers begin to respond, and it is definitely going to be very interesting to watch. Now, Core Technique wants to hear what you think. Do you believe a hybrid system with 48% efficiency is the smartest bridge toward a fully electric future? Or do you think pure electric vehicles will leapfrog all of this faster than anyone expects? Leave your answer in the comments below. I read every single comment. See you in the next video.